let's burn through some convergence and divergence tests. First, let's consider, was that 6 to the n over n? And I was going to use the ratio test, but you all pointed out that it would be better to use the ratio test. Or sorry, I was going to use the ratio test, but you said to use the comparison test, which I think is actually the much better way to go about it. Right? So, actually, we should say use it with 1 over n, whose harmonic series diverges. Since 6 to the n over n is greater than 1 over n, our series diverges as well. Okay, that's all it takes. Let's look at number 2. All right, we've got that. -1. Okay. We've got to start this series at 2, right, or else we're dividing by 0. Not cool. And this is clearly an alternating series test. Now, if I'm just asking for convergence or divergence, then use the AST and be done. Let's assume we're asking for absolute or conditional convergence, okay? So I'll just say, I'll say since 1, the limit as n approaches infinity, that's infinity of 1 over, I said ln of 2, so that should be ln of n. 1 over ln of n, that equals 0. And 2, 1 over ln of n plus 1 is clearly less than 1 over ln of n. Our series converges, right? Remember, AST is only a convergence test. It is not a divergence test. Okay? Now to see whether we get absolute or conditional convergence, consider this series. 1 over ln of n, right? Drop the negative ones again. Drop the alternation. Again, we're going to compare to a p-series. In fact, again, we're going to compare to 1 over n. Use the comparison test with, again, 1 over n, whose harmonic series diverges. All right, so since, so again, this guy is bigger than this guy, right? ln of n is less than n, so 1 over ln of n is greater than 1 over n. So our series has to diverge as well. All right. On to number 3. Oh, the arctan for n squared. I guess that was starting at 1. Doesn't really matter where we start at in terms of convergence or divergence, right? This stuff converges or diverges at the tails. Maybe I'll give this a little bit more room here. So what should we do for this one? What did we say? I wanted to use the comparison test. Yeah, or the LCT, right? I actually think the I think the LCT is a little safer, but really it's fine either way you do it. But use it with 1 over n squared, whose p series, right, p equals 2, converges. Okay. All right, so since the limit as n approaches infinity of, I'll do it a little bit closer, arctan of n all over n squared divided by 1 over n squared, multiplied by the reciprocal. Right, of course, these are going to cancel. since this equals pi over 2, which does not equal 0 or plus or minus infinity, our series converges. Okay. Number 4, right? Sine of 1 over n, yes. This sneaky one right over here. Sine of 1 over n. Right, might be tempted to try the test for divergence, but that doesn't work. You get 0. Turns out, use the LCT again. And with 1 over n again. Actually, it turns out that this works. Whose P series, or maybe I should say harmonic series to be consistent. Harmonic series diverges. Okay. All right, so since, again, this is a little bit sneaky. This would take a little while to see, right? Right, this is 0 over 0, which means we get to use L'Hopital's rule. Right, but since this leads us to the limit as n approaches infinity of cosine of 1 over n times the derivative of 1 over n, frankly, it doesn't even matter what the derivative of 1 over n is because we're dividing out by it down here. But it's good to know our derivatives, come on, right? But since this limit equals 1, which last I checked was not 0 or plus or minus infinity, our series, maybe somewhat surprisingly, diverges. Okay, that's how you do that one. A little sneaky there. Oof, well, there's a mess. 10 times negative 1 to the n, 4 to the n. So, oh my gosh, let's see if I can remember that one. I think the longest part of this problem is going to be just writing it all down. All right, let's see how good my memory is. Something like 10 times negative 1 to the n times 4 to the n all over 7 to the 3n plus 2. Did I get that right? Yeah, I actually did get that right. Oh, man, that's awesome. All right, well, first off, let's rewrite this. Let's make this a little bit better. Let's rewrite this as the sum, 1 to infinity, of, okay, so maybe let's shave some stuff off first. I'm going to write 10 over 7 squared, or 49, whatever, times negative 4 over 7 cubed to the n. Do we see that? See what we did right there? And actually, even that's not really ideal. I have a ton of space here. Right, because this is going to equal, I'll just do it down here. I'll do it over here. This is going to equal the sum from 1 to infinity. 1 to infinity of, actually, it's going to be negative 40 over 7 cubed times negative 4 over 7. Oh, shoot. Actually, sorry. That's not 7 cubed. That's 7 to the 5th. To the n minus 1. Right? That's still a 3 right there. Right? We had to take out a factor of negative 4 over 7 cubed. We had to take that out. All right? So we have that. And because r is less than 1, right, since r equals, I should say, since it's between negative 1 and 1 would be the better way to say that. We have convergence 2. We actually have the value, like we can actually write what this converges to. It's negative 40 over 7 fifths divided by 1 minus, I guess it's going to be plus 4 over 7 cubed. Yuck, I don't want to figure out what that is, okay? But that's what it equals. I probably should make this a complete sentence. This is a geometric series. All right. Hopefully that's recognizable as a geometric series. All right, raising a bunch of stuff to the end. Okay. All right, and last but not least, I think my color coordination's a bit off. Oh well. Number 6 just reeks of the ratio test. N and factorial. All right, so number 1 actually, well, you don't even need to use the ratio test if you're a little bit clever, right? Because if you're really clever, then you can notice, maybe not really clever, but if you're good with your factorials, right? Maybe you can notice that that's how that cancels. You should still probably use the ratio test, but you could even get away with a comparison or limit comparison test, potentially. Maybe a comparison. It's just easiest to use the ratio test. Let's just use the ratio test. But it's still good that we simplified that. And even if you didn't, then you'd still be fine. Right, limit, I'll say since the limit as n approaches infinity of absolute value. Always include that absolute value, right? And we're doing n plus 3, n plus 2, times n plus 2, times n plus 1. Right? And, you can group things if you'd like. Might be a good idea. Takes an extra minute. I think it's worth it. Need to. Right, this cancels pretty nicely. That all cancels. And we just get 2, which is greater than 1. So our series diverges. Right, so the factorial on the top, factorial on the bottom, right, they sort of cancel each other out pretty much. Cancel each other out. So, like the top was sort of most of the terms of the bottom, so that's what we get. Right. So just to show you, this is how to do these convergence and divergence tests, right? We did 6 in not a whole lot of time. Now, granted, we did know which tests to use, but if you're good with the tests, then it shouldn't take you all that long.